Good afternoon. Am I audible?
Yes, ma'am.
Okay. So I'll wait for a couple of more minutes. If somebody else joins, then we'll start off. Is it fine? I'll start sharing my screen. Please let me know if you can see it.
Yes, ma'am.
Thanks. You can see the PPT, right?
Yes, ma'am.
Okay. Okay, it's 5 minutes past 4. So I'll just start. So, hello, I'm Shreya. I'm the TA for this course. So, last week, somebody had some questions regarding the reference books. So, sir had also suggested these. You can follow Draper and Smith and Montgomery for understanding this course in more details. And now, did you go through the week 3 lecture? Sorry, I'm not able to hear you. Can you be a little louder? Okay, Vaibhav. Then you might face some difficulty, but I'll try to explain as I work along and solve the sums. So just hang in there, okay? Yes. Okay, so I'll just start. So these are the reference books that were suggested, and previously we learned how we should fit a multiple linear regression. So for a multiple linear regression, there would be one response variable and several predictor variables, and we would fit something like this. This would be my multiple linear regression model. In case of simple linear regression, we would have only one predictor. In case of multiple, we'll have more than one predictors. So in order to fit such a regression, we had to find out estimates of these things, like y hat would then be beta naught hat plus beta 1 hat x1 plus this one, and these estimates, these would be obtained by minimizing the, this is the fundamental idea, to minimize the residual sum of squares of errors, residual sum of squares. Up till this, is it clear? I hope this is clear to you, Vaibhav.
Yes, ma'am.
Okay. So, going along the procedure, how we were finding the, how were we minimizing the residual sum of squares? We were taking this thing, summation ei squares, and we were taking partial derivatives with respect to each of the parameters, and we were equating them to 0, and that would give us the estimate of, and here we would have a set of equations, and from there we would get an estimate of beta. So this was the fundamental idea. So here you see we have 1 to k minus 1 and beta naught, k parameters that need to be estimated. So in that case we would have, these were the normal equations. So in this case, with k parameters, we would have k normal equations, and after solving them we would get the estimate of beta, that is each individual element of this vector would be an estimate of beta naught, beta 1 and beta k minus 1 respectively. So we learned this, how we should fit a multiple linear regression. Next, what was done in week 3 was that, suppose we are fitting this regression, y equals to this one, beta naught plus beta 1 x1 plus beta 2 x2 plus, let's say, beta k minus 1 xk minus 1. Let's say this was the model, and we have fitted, we have calculated y hat, and we have got the predicted values of, we have got the estimates of these k parameters, that is the betas. Now if we had to test for the significance of regression model, what we were essentially testing was that beta each of these equals to 0. Versus h1 at least one beta j not equal to 0. So whenever we are asked to test for the significance of a regression model, this would be my criteria. this would be the h naught, that none of these variables are significantly different from 0, versus at least one is not 0. If all of these are 0, it means that the x's do not have any effect on y. But if at least one is not 0, then some of the variables, some of the predictors would have an effect on y. Okay, so the way to go about this thing was, one of the way was to construct the ANOVA table. And how we would do that? We would just write down the sources of variation. One would be regression, one would be residuals, and this would be total. Then our degrees of freedom, this would be n minus 1, this would be n minus k, and this would be k minus 1. Why so? Because this total sum of squares, we have seen it can be split into sum of squares due to regression plus sum of squares due to residuals. And since in the first class itself we have seen that summation yi minus y bar, this is 0, it means that all the y's, we can only choose n minus y's independently, because the last one y would be chosen so that this constraint is satisfied. So SST would have a degree of freedom of n minus 1. SS residuals would have n minus number of normal equations or number of parameters that we have estimated. So here we would have k, and due to the additive property, this one would have a degree of freedom of k minus 1. And then we would jot down the sum of squares, and then we would do the mean square. The formula would be sum of squares divided by df, and we would calculate the f statistic, which would be ms regression by ms residuals. And if this value is greater than the critical point at alpha level of significance with a df of k minus 1 and n minus k, then we would say that the regression, we reject h naught and say that the regression model is significant. Okay, if you follow the lecture notes, I'm sure you will be able to follow. And then after testing for the significance of the regression model, so initially we had beta 1 to beta k minus 1 equal to 0, versus h1 was at least, this was previously what we tested, at least 1 beta j is not equal to 0. Now the next question is, so we saw that h naught was rejected. That means there are some beta j's which are significant. Now if we have to find out which of the parameters are significant, then we can conduct testing, this significance testing on individual regression coefficients. And this beta j hat would follow normal beta j and sigma square x transpose x inverse, the jth element of this matrix. And then, like we tested earlier, this beta j hat minus beta j by this one root over sigma square x transpose x inverse jj would follow a normal 0 1, and then we would estimate sigma square by the mean we would estimate it by the MSE, and then we would test as usual. So I'll do 1 sums of each, you will be able to understand then. And then we also saw how this extra sum of squares technique can come in handy when we have to test a set of regression coefficients. So let's say in this model plus beta r x r plus beta r plus 1 x r plus 1 to beta k minus 1 x k minus 1, something like this we have. So if our h naught is, let's say, the first r this is 0. So if instead of all zeros we are to test a subset of this thing, then our test statistic would be, we would compute sum of squares due to regression with the full model when nothing is 0. We'll fit everything, we'll get the estimates and the sum of squares by fitting the entire model. And then minus, we would do sum of squares due to regression as per the restricted model. Now the restricted model will only have y equal to beta naught plus beta 1 x1 plus beta r xr, something. This one divided by r and our sum of squares due to residuals from the full model by n minus k. This would be my test statistic, and which under h naught would follow an fr n minus k, and based on the critical point of this distribution we would take a decision of what to do, to reject h naught or to accept h naught. So all of these were covered in week 3 lectures, and then one question was also solved, that also you please go through. And then finally what was done was the confidence intervals of the beta j's and prediction interval of y. Like suppose if you are given some x value, x1 equal to something 10, x2 equal to 30, and xk minus 1 equal to something, let's say 27. Then with this given values of x, okay, yes, so with these given values of x we would have to get a certain 95% say prediction interval of what would be the value of y if these were my x's. So these things have been covered in week 3 lectures. So even if you have not followed the lectures till now, I'll solve problems so that when you go back and follow them it will be easier for you to relate. Is it fine for everyone?
Yes, ma'am.
Okay, thank you. Yes, so I'll start with a very simple problem, and I would urge you to calculate and solve this along with me. Okay, so here I have one y and two x's. So this is a multiple regression problem. So our model is given like this. we are to fit y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. So what would be the estimates of beta naught, beta 1 and beta 2? So the first and foremost thing is to write this down in terms of the formal matrices. So let us define a y vector. This would be my vector of observations. So what would be the dimensions of this vector? There are 1, 2, 3, 4, 5, 6, 7, 8. So it would be a 8 cross 1 vector. Fine. So let us write this down. This is 66, 43, 36, 23, 22, 14, 12 and 7.6. This is my y vector. We are to fit a model y equal to x beta plus epsilon. So this can be written like one, 8, 1 into beta naught, if I am writing in this manner, plus 38, 41, 34, 35, 31, 34, 29, 32. This into beta 1 plus 47.5, 21.3, 36.5, 18.0, 29.5, 14.2, 21, 10 to beta 2. Then we can write this 66 equal to beta naught plus 38 beta 1 plus 47.5 beta 2. For each of the yi's, we can then the entire equation for each of the yi's, I am representing it in this manner. This one I can also write as this thing, (34, 32, 47.5, 21.3, 36.5 and so on till 10. This one to beta naught, beta 1, beta 2. Even then we can say that 66 equal to beta naught plus 38 beta 1 plus 47.5 beta 2. I hope so far is clear. Then what we are having essentially, this is my X matrix and this is the beta vector. So here what is the order? The order is 8 cross 3 and here this is 3 cross 1. Plus we have some epsilons. Let's say epsilon 1, epsilon 2 to epsilon 8. Okay. Now once we get our X matrix, so from normalizing from the normal equations and by doing derivative, by taking derivative over all beta j's, we would obtain beta hat equal to x prime, x transpose x inverse, x transpose y. This is the formula to get beta hat. Now we have our x 1 1 something. This one would be, okay, I'll write it down, 1 1 1 1 1 1 1 1, 8 ones. Then okay, I'll just point you to this. This is my X matrix. So the first column will be 1, the second column made of this x1, and the third one made of x2. So we are to compute this thing, x transpose x inverse x transpose of y. So will you please calculate it? And tell me what you are getting. Okay, I would, yeah, say.
Can you please go on previous slide?
Oh, it's gone? Okay, okay. Okay, so inverse calculation I think will take a lot of time. You can just match it with what I've written over here. Okay, so this I'll post these slides. You just check it and see if it matches or not. So our X transpose X, see X was an 8 cross 3 matrix, right? This one. So X transpose would be a 3 cross 8 into a 8 cross 3. So ultimately we have a 3 cross 3 matrix. So X transpose X inverse will be something like this. This will also be a 3 cross 3 matrix. And finally my beta hat would come out as this one. So this value is the estimate of beta naught hat. This one is the estimate of beta 1 hat, and this is the estimate of beta 2 hat. Okay, you just need to compute this thing. You need to, whenever you get such a sum, you just need to write down the X matrix and then compute this value, and then you would get a vector like this whose individual components will give you the individual estimates. So once we have understood this, I hope this is clear.
Yes, ma'am, clear.
Okay, you just go back and check how these this one is derived. It's very simple. It comes from the normal equations. Okay, so once we have our estimates, that is beta naught, beta 1 and beta 2, the next question is to find out the value of the residual sum of squares. So this residual sum of squares can be calculated simply or in this manner, in two manners. Either you can use formula or you can go to the basic, like you have some y, you will have y hat, which will be x beta hat. You take y hat minus y, and then you would have the residuals, 8 residuals you would have here, 1 2 3 4 5 6 7 8. You take the sum of squares. That is one method. And the second, this entire thing, if you do, then this S's residual formula, it comes as y transpose y minus beta hat transpose X transpose Y. Where Y was this thing, this one was Y, and X was this one, and beta hat we have obtained as this. So I'll just write it down. So Y transpose Y is nothing but summation yi square. This is a vector. This is also a transpose of a vector into that vector. It gives summation individual element square, this thing minus beta hat transpose. So beta hat transpose would be here were the estimates, minus 94.5 minus 94.5, then this one was 2.8, sorry, this one was 2.8, 1.07 into X transpose Y. That would also be a X transpose Y. X was a 8 cross 3 matrix, and sorry, X transpose would be a 3 cross 8 matrix, Y would be a 8 cross 1 matrix. So ultimately we would have 3 values over here, and this entire thing summation yi square, it comes out as summation yi square is 8911.76. This one is, this thing is 8911.76 minus this vector into X transpose Y. It comes out as beta hat transpose X transpose Y. It comes out as this entire thing. It is 8868.59, and this minus this would be something around 43.16. Okay, just plain and simple calculation, nothing fancy. You just have to remember this thing, how we have to calculate the sum of square due to residuals. Now if I have to find out the sum of squares due to regression, then I have to make use of the fact that sum of squares total equal to sum of squares regression minus, sorry, plus sum of squares due to residuals. Now I have this one and I need this one. So if I can anyway get this one, I'll just subtract and then I'll get whatever I want. So this thing is nothing but summation yi minus y bar whole square this thing can be written as summation yi square minus ny bar square minus sum of squares due to residuals. So ultimately this one was how much? In the previous slide we got 8911.76 minus 8 into y bar was 27.95. So 27.95 whole square minus sum of squares due to residuals was 43.16. Can you calculate this thing?
Yes, ma'am.
Yeah, yeah.
Twenty-six, 18.98.
Okay. So this is my sum of squares due to regression. So if you get a sum like this, so all you have to remember is you get the residuals, and it's very easy to get the sum of squares, total sum of squares, and we'll just subtract. This is just derivation. So this this concept has to be exploited for sums like this. Next, we are asked to find out the degree of freedom of sum of squares due to residuals. So here, total number of observations, we have 8, and our model was y equal to beta naught plus beta 1 x1 plus beta 2 x2. So how many normal equations? We do
Three
have
equation.
3. Then, so this is my k. So the degrees of freedom would be
N minus k.
n minus k, that is 8 minus 3, 5. Okay. Now, this question, the next one, it asks that what are the variance of estimates of beta 1 and beta 2? That is, they are asking for variance of beta 1 hat and variance of beta 2 hat. Now, if I consider beta normally, then this is beta naught, beta 1, beta 2. Beta 1 hat would be this thing. Okay, so if we have to derive it, then this is x transpose x inverse x transpose y. So we would see that epsilons, we have taken that epsilons follow IID normal 0 sigma square. So y would follow a normal x beta sigma square I. I is an identity matrix. Okay, so variance of beta hat would be x transpose x inverse x transpose variance of y into this entire thing transpose x transpose x inverse x, this transpose. So if we solve this, then we would get x transpose x inverse into x transpose, variance of y will be sigma square I will come here, and since sigma square is a scalar, it will come out, and then this entire thing we would have x into x transpose inverse. So then what we would end up with is sigma square, this thing and this thing will cancel, this thing, sigma square x transpose x inverse. So what I'm essentially saying is that variance of beta hat would be sigma square x transpose x inverse. So in this case, variance of beta hat would be sigma square into this matrix that we had. Okay, this one, this entire thing. Now if you look carefully, this is the variance covariance matrix of the estimated betas, where the diagonal elements are the variances and the off diagonal elements are the covariances. Like for example, this is the variance of beta naught hat, and this one is the covariance between beta naught hat and beta 1. So here we have been asked to find the estimated variance of what I just said, there's a correction. We have to multiply sigma square with these diagonal elements to get the variances of the variance of beta naught hat, beta 1 hat and beta 2 hat. So I'll just copy this thing, just give me some time. So this is essentially my variance of beta hat, sigma square into this thing, because this is x transpose x inverse. Now we don't know what the value of sigma square is, so we have to estimate it. So like I was saying, variance of beta 1 hat equal to sigma square into, this one was for beta naught, this one was beta 1, this one was beta 2. So this diagonal element to 0.01. Similarly, variance of beta 2 hat was this one, sigma square into 0.001. Okay, now we don't know what is the value of sigma square. So if I have to find an estimate of the variance, then I need to find an estimate of sigma square. Same here as well. If I have to find an estimate of the variance, then as we know that MS residuals is an unbiased estimator of sigma square. This holds true. We have seen that. So if we are to find out the estimated variance of beta 1 hat, then we just need to find out and substitute the MS residuals in this place. So SS residuals was how much? SS residuals, this was 43.16. So here we'll just put 43.16 divided by degrees of freedom. So n minus k, that is 5, this into 0.01. So this would be 8.63 into 0.01. That is something 0.0863. Here also it would be 8.63 into 0.001, 0.00863. Is it fine? All we have to remember is this thing. Variance of beta j hat equal to sigma square x transpose x inverse jth element, that is the diagonal element. Whichever beta I am finding variance of, that corresponding diagonal element we'll take from the x transpose x inverse matrix and we'll multiply with sigma square. So I went a little back and forth. I hope this is clear.
Yes, ma'am. Clear.
Okay. So the next thing is, if you get a question like this, that you consider the multiple linear regression and you're asked that how much of the variation y about y bar is explained by x1 and x2. So any idea what exactly, which quantity are they asking for? They want to ask, they are asking how much of the variation in y about y bar. So this one, something, how much of this is explained by this one, this quantity and this thing. So essentially what they are asking is, what is the coefficient of determination? This one explains what is, explains the proportion of variation in y about y bar explained by the predictors. So they are asking, what essentially they are asking for is the value of what is the r square. So as we know, r square is sum of squares total by regressions or residuals. Anyone? Okay, so r square is basically sum of squares due to regression by sum of squares due to residuals. Total sum of squares. R square is sum of squares due to regression by total sum of squares. How much of the total variation is explained by our regression? Okay, so the total one was 8911 point something. What was that? 8911.76. No, this one minus this. So this one was, I'll write it up fresh. Sum of squares was yi minus y bar whole square. This one could be written as summation yi square minus ny bar square. So this one was 8911.76 minus ny bar. I'll just calculate. $27.95. This one was 8 to 27.95 square. And sum of squares due to regression, we had calculated this. This one was 2618.98. 2618.98. Yeah. So how much is it coming to? would come to 0.9838, that is 98.38%. So our R square is 98.38%, which means that 98% of the variation in Y about Y1 is being explained by X1 and X2. Okay, so once we have this thing, let us consider this problem. Let's say we have my pen is not working. Okay, so you have to consider this multiple linear regression model, and they are asking if the overall regression is significant or not. So how we were to solve this problem is by constructing the ANOVA table. Okay, we would just make the ANOVA table. So sources of variation would be regression, residuals, and total. So degrees of freedom, total there were 8 observations. So this total DF is 7, and residual was n minus number of normal equations, that was 5. So this would be 2. And our sum of squares due to regression was 2618.98. This one was 43.16, and the total one was 2662.14. You can check this. So then we compute the mean square. Mean square due to regression would be 2618.98 divided by 2, would come to 1309.49, and this one would be 431.16 by 5, it would be something around 8.63, and our F statistic would be 1309.49 divided by 8.63, which would be something around 151.74. Okay, now our observed value of the test statistic is 151.74, and alpha is 0.05. that means we have to, our critical F that we need to consider is with degrees of freedom. I mean, this one would be an F distribution with degrees of freedom k minus 1, that is 2, 5, and the upper 0.05 level of significance. So this value we'll get from the table. So just see, let's suppose this is an F distribution. So we are to get this F star value such that probability of anything lying above this area is 0.05. So this is our P. In this case, in our case, it's 0.05. So first we'll look for and we want some F2 and 5. K minus 1, n minus k. This one is the numerator. Sorry, k minus 1, and this one is the denominator. So F2 in the numerator. Then this column we'll focus on. And we have 5 in the denominator. Then this one. So we'll focus on this block. Now what is my P that I want? I want 0.05. So my critical value is 5.79. So here if we go, this value is 5.79. Now since what would be our decision? Since our test statistic is greater than the critical point, because we have 151.74 and this is 5.79 only, so we will be rejecting H0, because this was our decision rule. If the observed value of the statistic is greater than the critical point at alpha percentage of significance, then we would reject H0. So is the overall regression significant? The answer is yes. Why? Because we were testing beta 1, this thing we were testing, but we are rejecting. So at least one of the betas not equal to 0. We are rejecting this one, that they have no significance, and consequently we are leaning towards H1. So if the question is the overall regression significant, we would say that yes, it is significant. Okay. Anybody there?
Okay, ma'am. Clear.
Okay. And one more question I have for today, that is, if you are given some point and you have to find out the prediction interval at some given point, how would you do that? So let's say we want to find out a value of y at x1 equal to 37 and x2 equal to 30. So in this case, my x vector would be 1 for beta naught, beta 1 x1 would be 37 and x2 would be 30. So we have to find out something which is x prime beta plus epsilon. Now this is the predicted value of y. Let's say this is x0. Okay, so y would have some margin of error and this entire thing. Now y predicted would be this thing. Then we consider another variable which is psi, and we denote it by y prime minus y. So then expectation of psi would be expectation of y hat minus expectation of y. Now this one would be expectation of y hat is this thing minus expectation of transpose beta plus epsilon. Now epsilons we know they follow this thing, normal 0. So this expectation and beta hat also we know is unbiased for beta. It's there in the lecture note, expectation of beta hat equals to beta. So this thing also we know. So here we would have x transpose beta minus this expectation would be 0 and this is independent, this is a fixed quantity, so we would have this, that is 0. Okay, and if we are to find out variance of psi, then this would be variance of y hat minus y. Now y hat is my fitted based on what I have now, and this y is my future observation. And since we have considered that this is independent, we can write it down as y hat plus variance of y. This one would be variance of this thing, x naught prime beta hat plus variance of y. Now this one we'll write as x naught transpose variance of beta into x naught transpose and transpose, that will be x naught, and variance of y, based because this is follows normal sigma square I, this one will also follow normal sigma square I, so variance of y would also be this one, and this would be x naught transpose variance of beta is sigma square x prime x inverse x naught plus sigma square. Then we would have sigma square x naught transpose x prime x inverse x naught plus 1. So once we have the variance and the expectation, all we need to do is we just need to compute this thing psi by root over variance of psi. This one would follow a normal 0 1, and this one would be y z naught hat minus y naught, sorry, I messed up the notation it seems, so y hat minus y, yes, so y hat minus y by root over, in place of sigma square we would write ms residuals, and this would be this thing plus 1. This one would follow a t distribution with degrees of freedom 5. Now we'll just write this one minus t5 0.025 less than this entire thing less than t5 0.025. This would be 1 minus alpha, and then keeping y in the center, we would just rearrange the entire thing and get some values over here, which would be 1 minus alpha, and these values would be then my prediction interval. So here I've calculated y naught hat would be something like this, and this major term will come out as 0.2, and this would be my 95% prediction interval for y. And after so much of calculation, it will come down to this would be in 95% prediction interval, and this t 0.025 with degrees of freedom 5, that we'll find from this t table. So two-sided 0.05 we'll take, and with this would be the df. So for 5 we have this value 2.571. This value I have substituted over here and I've obtained the prediction interval. Okay.
Okay, ma'am.
Okay, I can understand that this was a little difficult, but please go through the class notes and you'll be able to follow what I have done so far. I hope you'll be able to follow. And if you have any questions, you can post it in the discussion forum and we'll try to answer that. Okay, thank you so much for joining. I'll now stop the presentation and see you again next week, hopefully.